Next slide for presentations by Paul Hayne. Can we move on?
Everyone.
Thank you.
You hear me okay?
Yeah, we hear you good. Thank you, Paul.
Okay. I'm going to be talking about the utility of thermal infrared measurements for investigating potential resources in the form of lunar volatiles and ice in particular. So the tool of thermal infrared remote sensing has been used successfully in global remote sensing investigations to study the lunar surface temperatures and identify locations where ice might be stable. And this has been done quite successfully, as you can see in these plots here. So on the left is a figure from Elizabeth Fisher's paper showing the distribution of reflectance spectra as a function of temperature on the bottom axis for two different data sets. One is the LAMP, the ultraviolet albedo data on the left-hand axis in the dashed line, and on the right axis is the normal albedo from LOLA in near-infrared wavelengths. And what you can see is there's this distinct change in spectral behavior when you hit around 100 Kelvin or 110 Kelvin, which corresponds to the stability region for water ice. And so this has been used as evidence for the existence of water ice, but not only that, it's a very important constraint on the processes that sequester ice on the moon. So what this means is that essentially surfaces that are cold enough to have ice on them do have ice, at least in a patchy distribution, and those that are too warm do not. And too warm refers to the time scale over which that ice would disappear, which is billions of years. And so this may be pointing to potentially ancient reservoirs of ice that correlate with temperatures that are cold and stably cold over long periods. And the right-hand side shows some examples of maps of those points, including using LAMP and M-cubed. Next slide, please. So in terms of the actual measurements, we've done this with global remote sensing with the Diviner instrument, which is a multi-band infrared radiometer that creates push broom images or mapping at about a 250 meter resolution scale and in the average orbit altitude. The sort of next iteration on this will be L-Sirius, which will be deployed near the lunar South Pole, planned for 2023 as part of NASA's CLIPS program. And then also a similar instrument on lunar Weiss, which was recently selected to go to the Greenhagen domes. And that's a typo there that should have been surface mapping at centimeter scale. I apologize for that. So L-Sirius will get centimeter scale resolution on the surface around the landing site at both of these locations. Next slide, please. So one example of a coordinated campaign that we could perform to investigate where ice might be stable would be to look at the micro cold traps. So on the lunar surface, it's hard to wrap your head around it, but the thermal gradients on the moon can be much more extreme than what we're used to on Earth. And so you can get these extreme gradients on scales down to centimeters. And so if the supply rate of water at the geologically present time is sufficiently high, then the micro cold traps should be full of ice. If it's not, and the destruction processes outcompete the supply rates, then the ice won't be there. And so the measurement of volatile content in those micro cold traps, which would combine thermal infrared and near infrared or other compositional measurements, could actually determine the present day supply and destruction rates. Final slide, please. So as an example of how you'd actually do this in practice, you'd measure the spatial scale of the PSR, measure its temperature and the water content. The separation between these curves would show you essentially the difference between the supply and destruction rate. So the coupling of these different types of measurements would be a very important and critical set of measurements to make for resource evaluation. Thank you.
All right, thank you, Paul.